So today we're going to talk about a very interesting property of Poisson process in variables in general. So it's called the thinning. It's in the heart of several interesting constructions made with Poisson processes, and it's a very surprising fact. So suppose that we have a Poisson variable x or z maybe, so distributed as Poisson with parameter lambda. So this can be seen as a box full of k of z balls, and we have a number of balls being distributed as a Poisson lambda random variable. And what we're going to do now is to split this into several different boxes. So we're gonna reorganize them into smaller boxes. So to do this, we need extra random variables. So the number of boxes is gonna be 1 up to n. And we're gonna have these extra variables xi, which are independent, actually IID, distributed as nu with a probability on 1 to n. And x tells you where the ball I goes, to each of these bins it goes. And what we are interested in is in the distribution of the number of balls that end in each of these boxes. So for this we need to define a bit better what is the random variable. So we have y1 up to yn. These are going to be the number of balls in a bin 1 to n, where yj is just the sum for I from 1 to z. So we take all the balls, but we just sum something if xi is equal to j. So we just count the ones that have x equals j. And this gives us the amount of balls in the bin number j. What the next lemma tells us is that under the above circumstances, yj are independent and yj is distributed as another Poisson random variable with parameter lambda times nu of j. Okay, so this, if you're not surprised by this, you should read it again, because this is a very surprising fact. We started with a bin with a fixed number of balls, z, and distributed these balls into different bins. And by the end, the number of balls that fall in each bin is independent and has the same distribution as the original bin with a different parameter. So this independence is surprising, to say the least. So this is something we should think a bit about. Now for the proof, this is actually very easy. After you know what you're looking at, it's very easy to prove. So first we take we have to estimate the probability. So we're going to do this for n equals 2, okay, because it's really easy to extend. So now we want to look at the probability that y1 is k while y2 is l for some k and l bigger or equal to 0. And this should break into a product, right? So here this is by definition we have to we can break it into the sum of the same probabilities, but also looking at what the value of z was. And z can be any, let's call it I. Okay, but I, for this to happen, have to be exactly k plus L, because here we are splitting k to one side and L to the other side. There are only two beings, so we started with k plus L. So actually only one term of this sum is not going to be 0. It's going to be the k plus L term. Okay, so let me just increase the size of the canvas here. So this will give us z has a Poisson distribution, so lambda to the k plus L, e to the minus lambda over k plus L factorial. Now, given that z is equal to this number, the y's are independent of z. I should have, so the x's are independent of z. So what is happening here is that we have a sum over all the possible choices g contained in 1 up to k plus L, such that the size of g is equal to k. So after we fix this, what we need is all the x's x j is equal to 1 for j in G, and all the x j's are equal to 2 for j not in G. And these x's are independent of z, so that's why the probability of z went outside. So I'm just repeating this. And here we have x's which are IID, so this grouping doesn't matter. What matters is the number of such choices. So we're essentially taking k plus L and choosing KL of them. And fixed such a choice, the probability that k of them turn out to be 1 is nu of 1 to the power k. And we still have nu of 2 to the power L. Now this I'm going to define as P. So this is going to be P to the K, and because nu is a probability measure, the other is 1 minus P. So now what we have, we can group the things together. So lambda to the K groups with the P to the K, and it becomes lambda P to the K. E to the minus lambda, I'm going to write it as such, which is kind of silly, but it works. The binomial coefficient, we're going to write it explicitly. It's k plus L factorial over k factorial, that I'm going to write here, and L factorial, that I'm going to write here. And we still have 1 minus P to the L, and we still have the k plus L factorial in the denominator. These terms clearly cross. Here I'm forgetting something. Oh, there's still a lambda to the L here that I forgot. And in the end we get the thing very well grouped. Lambda P to the K, e to the minus lambda P over k factorial, lambda 1 minus P to the K, 1 minus P, sorry, e to the minus lambda 1 minus p over L factorial. Sorry, here is L. Is this correct? Yeah, the lambda to the L here and the 1 minus p to the L. So in essence what we've got in the end is the product of the probability that a Poisson lambda p is equal to k times the probability that a Poisson lambda 1 minus p is equal to L. So indeed these two variables have the correct distribution, which is Poisson lambda times its probability, and they are independent. This probability broke into a product for every k and L, so this is indeed proving the independence as well. So the thinning, why is it called thinning? Because one corollary of this is that if Z has Poisson distribution and x's are IID Bernoulli random variables, then the number of variables Z that were a success. So here we start with the Poisson process and we just give every of these points a chance. They have to toss a coin and survive or not. And here we count all the successes. This can be seen as take all the Z random variables and send to two different bins, the success and the failure. And this is the number of success bins. So it has a distribution which is Poisson lambda p, because you're just taking the above statement and summing over the right variable, the y2, and since y2 is still, since this is an independent thing, we just get the probability of the first one, which is Poisson lambda p. So that's why it's called thinning, because we start with a Poisson point process and we thin it a little bit by killing the ones that came to the failure box, and what's left, the survivals, are still Poisson with just a thinner parameter, lambda times p. So this is a very powerful property of Poisson process, and we're going to use it a lot in the next lecture when we start to describe the Poisson point processes. So see you next class.